Okay, so we are going to talk about a topic called vapor pressure. Vapor pressure is actually covered in chapter 11, part 3 of your textbook. And sometimes we cover it in the gas chapter, and sometimes we cover it in thermodynamics because it kind of fits in both chapters, but it's in a different chapter, and I'm going to go ahead and cover it here, and we will talk about it some more later. But first, let's just define vapor pressure. So what vapor pressure is it's the pressure of a gas above a liquid. So we talked about vapor pressure when we talked about intermolecular forces at the end of 161. So let's just think about that for a minute. So if I say here I have a beaker and it has water in it. So here it has liquid water. Above this liquid water here, there is some gaseous water molecules. And the amount of gaseous water molecules above this liquid water is what determines the vapor pressure. The vapor pressure is dependent on what the heat of vaporization is, how much energy it takes to go from a liquid to a gas, and the temperature of this liquid. As the temperature of this liquid increases and these molecules are becoming more and more excited, the vapor pressure is also going to increase because more of these liquid molecules will evaporate and escape into the gaseous phase. So there's a formula that we can use that relates the vapor pressure of a substance to the temperature. And this formula is called the Clausius-Clapeyron equation. So the Clausius-Clapeyron equation looks like this. It's the natural log, ln, of P2 over P1, so this would be like final pressure and initial pressure, equals the enthalpy of vaporization, the heat of vaporization, over R, times 1 over T1 minus 1 over T2. So let's just define some of these things. So we said P, this is pressure. And it doesn't matter what unit this unit of pressure is in because they're going to be the same, so they're going to cancel each other out. So if you were solving for one of these other pressures, then it would be in whatever unit the other pressure is in. So this unit can be any unit. The heat of vaporization is always given in kilojoules per mole. R, because heat of vaporization is an energy, it's a heat, because this is a unit of energy, a joule, that means my unit of R is not going to be the 0.0821 liter atmospheres per mole Kelvin. It's going to be the 8.314 joules per mole Kelvin. Because anytime that we have anything with energy in it, we're going to use this R constant because it also has a unit of energy in it. So one thing you're going to want to pay attention to is that you either need to change your R to kilojoules, or when you solve for the heat of vaporization, it's going to be in joules, and then you would convert it to kilojoules. You just need to be aware that this kilojoules and joules, that needs to be justified somehow. You need to convert one or the other depending on what the question is giving you or what the question is asking. This here, T1 and T2, initial temperature and final temperature, this is temperature, and this does have to be in a unit of Kelvin because my R constant is in a unit of Kelvin. So let's look at an example and see what kind of stuff we can learn and talk about with this Clausius-Clapeyron equation. Okay, so this here is a question. And I'm just going to write it over here just so we have some more space. It says the vapor pressure of diethyl ether, which also we just call ether, the vapor pressure of ether is 439.8 millimeters of mercury at 20.0 degrees Celsius. The heat of vaporization is 29.2 kilojoules per mole. What is the vapor pressure of ether at 34 degrees Celsius? Okay, so let's just kind of pick the information out that's in here. So what is the vapor pressure? The vapor pressure of ether is 439.8 millimeters of mercury at 20 degrees Celsius. So that's my P1 and my T1. So I'm going to say P1 equals 439.8 millimeters of mercury. T1 equals 20.0 degrees Celsius. It says the heat of vaporization is 29.2 kilojoules per mole. It says what is the vapor pressure, P2, what is the vapor pressure at 34 degrees Celsius? T2 is 34.0 degrees Celsius. So now I have everything that I need for this equation. I know R, so I've got everything I need. Things to pay attention to. You are going to be using R in joules, and you're going to be using the heat of vaporization in kilojoules. So I am going to go ahead and just convert this joules to kilojoules, or you could convert joules. I'm going to convert kilojoules to joules, but you could do either. Another thing that you need to pay attention to is you need to convert degrees Celsius to Kelvin. So this becomes 293 Kelvin, and this becomes 307 Kelvin. Okay. So I'm going to go ahead and put these in. So I'm going to say the natural log of P2, which I don't know, over P1, which is 439.8 millimeters of mercury, equals the heat of vaporization, which I'm going to go ahead and convert to joules. There's 1,000 joules in a kilojoule, so 29.2 kilojoules times 1,000. There's 2,920 joules, so I'm going to say 2.92 times 10 to the third joules per mole. So again, I converted this to joules because my unit R 8.314 joules per mole Kelvin. You need to convert one of these, it doesn't matter which, times 1 over T1, 293K, minus 1 over T2, 307K. So now I'm just going to solve for P2. So I'm going to do this whole side first. So I'm going to go ahead and do that. So I'm going to say this part, 1 over 293 minus 1 over 307 times 2.92 to the third over 8.314. And you should get something over here. This whole side is going to be something like 1.727. And then over here, I have the natural log of, hang on just a second. Let me double check this. Yeah. So you should have something like 1.727, and then over here you have the natural log of P2 over 439.8 millimeters of mercury. So now to get rid of this natural log, on your calculator there's the natural log button right here, ln. This is not the same as log. This is a base 10. This is exponentiated. So we're going to use the natural log to do the opposite of the natural log. It's e to the x. So I'm going to raise both sides to this e to the x to get rid of that natural log, e to the 1.727. So I'm going to say second natural log, so it's e, and then I'll say 1.727, and that's going to be, whoops, it's E, hang on just a second. E natural log, E 1.727, 5.6. Sorry, I did the wrong thing. That was the answer. This whole side over here should give you something like 0.5463. And then when you exponentiate it, I was looking at the wrong part of my notes, you will get 1.727. So this whole thing is 5.5463. You're going to raise both sides to the e, and now you will get final pressure over 439.8 millimeters of mercury equals 1.727. So now I'm going to multiply both sides by 439.8 millimeters of mercury and you should get about 760. It's going to be about 759.5 with 3 significant figures. We really should get 760, but it's technically 759. So what is this? This is the vapor pressure at 34 degrees. So at 20 degrees, the vapor pressure is 439. At 34 degrees, the vapor pressure is 759. So something to pay attention to, and something that we learned about vapor pressure back in 161 when we talked about intermolecular forces, is that the vapor pressure equals atmospheric pressure at the boiling point. So one thing that may or may not, a red flag that may or may not arise, is that 760 millimeters of mercury, which is almost this, is 1 atmosphere of pressure. This is atmospheric pressure at sea level. So let's just go ahead and assume that this is atmospheric pressure. If this is atmospheric pressure, what that tells you and what you should be able to understand from this problem is that the boiling point of ether is 34 degrees. because that's the temperature where the vapor pressure equals atmospheric pressure. And by definition, that's what the boiling point is. And this was all covered back in the first section of general chemistry. And now this is just some calculations for us to relate pressure, temperature, heats of vaporization, to learn a little more about vapor pressure. So this is in chapter 11, but it is going to be, you are going to be responsible for this in this section of material. So vapor pressure, Clausius-Clapeyron equation, solving for different vapor pressures at different temperatures, or if you were given two pressures and two temperatures, you could solve for the heat of vaporization.